nth level solution in one norm. So these are in general discussion about the L2 norms stability as well as the L1 norm stability. So far we discussed in the last lecture as a in the beginning of today's lecture. So let's look whether these schemes are monotone schemes or not. So what is the meaning of monotone schemes? Then how do we say or define whether the scheme is monotone or not? If you look at the so far, a simple case here that we are always writing un plus 1 level solution as some kind of summation term, which is I can write down as summation of some coefficients aj into un something j plus m in general. So now what we are writing, so unj is some function of all the n plus 1th level solution at point j is can be written as function of all the previous level entries from some left values to the right values. L suffix L is left values and L suffix R is the right values. For example, if you see forward time and forward space. So for example, if this is the unj plus 1, so we are using in the backward space, forward time backward space, we are using this, and forward time we are using this. So we are computing the solution at this point is based on the grid values evaluated at this level. So n plus 1th level solution is depending on some if you are starting with the j is a some fixed norm, so you are moving to the left values as well as you are moving to the right values at most. This is the function some h function is depending on all these grid values, so which we are writing as some coefficients here bk. This h function we are writing as summation over all values from this left node to the right node here. Now if you are able to write down in this way, this is the next step is just opening the summation, and if all values we are talking about this bk, so all these coefficients are positive or not. If they are positive, then we are saying this scheme is monotone. So scheme of the form this equation is said to be monotone all coefficients positive. Alternatively, we can also say if it is a function, if this is a function h, then you can do a differentiation with respect to each grid point. Then if you do that, and when you get all the derivatives with respect to each grid point is greater than or equal to 0, then obviously we can talk about h is increasing function in each of its arguments, then we can say it's a scheme is monotone. So why this is called as a monotone actually? So in general the wave is here. We will talk about how to do with this with respect to one example first, then we'll come back to the physical significance. So let us talk about the affine scheme. Now this is forward time backward space and forward time forward space we are writing as an affine scheme. This is what we have shown in last lecture. This is an affine scheme now for any value of a. So a plus is positive and a minus is the negative. You can see forward and backward space. So we can write down this affine scheme in terms of some coefficients. Collect all the coefficients of unj minus 1, unj and unj plus 1, and whether the each coefficient associated to it is positive or not. So now let's see if you look at we are writing a plus into delta t by delta x as lambda plus, and a minus delta t by delta x is a lambda minus. Now if you see unj containing a plus as well as a minus them, so we are writing this as a modulus symbol. Obviously we know all this a plus is nothing but maximum of a comma 0, and a minus is okay minimum of okay a comma 0, and we also define a plus is nothing but 1 by 2 into a plus mod a, and a minus, right, a minus is nothing but 1 by 2 into a minus mod a. Okay, these are the okay quantities. With this we can write down any append scheme in this form. Then okay, the first coefficient if you see okay minus 1, okay, this is a okay minus 1 coefficient, j is okay, this is a b0 okay u and j, and this is b1 okay into u and j plus 1, this is okay b minus 1 into u and j minus 1 coefficient. So this can be written in the form of okay h is a function of u n j minus 1 and u n j and u n j plus 1. Okay. Now, okay, whether this each coefficient, okay, b minus 1 or b0 or b1 or 2 or not, okay, b minus 1, it's a lambda plus we can write down as a maximum of lambda comma 0, which you can write down as okay 1 by 2 into lambda plus modulus lambda. Okay. Obviously, if you see lambda is always bounded by 1, okay, so this quantity is okay positive quantity if you see, okay, and b0 it's a 1 minus modulus lambda, so this is also a positive quantity as long as lambda is not equal to 1, and b minus, so minus lambda minus, which you can write down as minus of minimum of lambda comma 0, then this is minus of lambda minus modulus lambda, so you can write down as okay 1 by 2 into modulus lambda minus lambda. Again the first quantity is positive okay always, and this may be less than equal to 1, so obviously this is also going to be a positive quantity. So all the coefficients are positive under this condition, okay, the CFL condition, okay, within this we get monotone scheme. Okay, so here one exercise you can do okay with the help of okay this thing, verify all the schemes, okay, forward time backward space, forward time forward space, forward time center space, Lax Frederick, okay, Lax Fedorov, okay, maybe beamforming and Fromm schemes, whichever we introduced for this okay linear advection equation so far, verify whether they are monotone or not. Okay, there is a physical significance that we will come back later. Okay, why we are looking at the monotone schemes. Okay, yeah. So this is fundamental so far. Okay, we looked at okay finite difference schemes, and we studied the consistency as well as okay stability so far. So there is one particular okay okay result by okay Pitlax okay given by this consistent finite difference method for a well posed linear PDE. So the method is convergent depend only if it is stable. Okay, so we have seen the consistency analysis of the linear PDE. Okay, this is well posed PDE now. Okay, and we have seen this TT. Okay, consistency plus stability can give the convergence. Okay, as long as the okay PDE is linear, but for the PDE is non-linear, there is no such theory. So one has to go okay with the different kind of techniques now. Okay, it is not straight. So let us see the okay solution structure of linear okay advection equation with the help of the modified equation. So far we have seen in many different ways. One is okay a priori energy estimates, one is L2 norm estimates, another one is L1 norm estimate, and okay one by method of characteristics from analytical techniques. Now let us see the story from the modified equation analysis. So what it is going to tell us in general. Okay, so when we do a simple okay Taylor series expressions. Okay, so far we have not done this. Okay, we have constructed finite differences and kept it, and okay reading it as a scheme, and we are we have implemented code also. Yesterday we have seen some schemes may work, some schemes may not work. Okay, now where it is going wrong, how to analysis now. Okay, so the first thing is okay we can start with the okay modified equation. Okay, let us say now okay see the modified equation tells us that original PDE approximates the okay exactly or not. Okay, this is the first question, and okay the answer to this is nothing but okay modified equation analysis. Again okay we have given okay linear advection equation with the okay initial data Okay. So the simplest case is forward time backward space. I'll try to extend for one scheme, then you can do for all. Okay, again. So it's a lengthy, okay, computation. Yeah, hold it. Okay, so this is a forward time backward space. Then okay, we are expressing this coefficient, okay, as well as okay UNJ. There is no need to do okay anything with respect to the Taylor series extension. This is already there at n and j, so we have to do it n and j minus 1 also. Okay, so un plus 1j, this is a Taylor series expansion, okay, with respect to the time. Okay, un plus 1j, okay, about a time. So unj plus, okay, this is the partial derivative of u with respect to t into delta t plus, okay, double derivative with respect to, okay, u uh, and delta t square by 2 and so on. This is for space, okay, j minus 1. Okay, so unj and okay minus delta x into ux jn and uxx, okay, delta x square by 2 and so on. So once we go back and substitute, okay, once we go back and substitute into the corresponding finite differences, this is the, okay, you can see, okay, this finite difference is approximating to the ut and all other, okay, finite difference scheme is approximating to the ut, and this now our truncation error term. Okay, okay, truncation error term. Okay, now okay, when we do okay this, okay, so what we are trying to do, this is what we required at jn position, okay, x, okay, with the minus sign and shifting everything, okay, to the left hand, okay, multiplied by a, because our ODE, so whether the okay, linear advection equation is going to be okay give us some other information other than okay what is the advection only. Okay, so what we are doing, the first case is differentiating with respect to t and x. Okay, this is the first equation. This is with respect to t and this is with respect to x, and replace all the okay time derivatives, space derivatives, everything. Okay, that's what the okay a big computation. So this is you have to do. This is your job to get. Okay, when you replace all the okay time derivatives and mixed time derivatives with respect to space also as well as time, okay, time also, replace everything. Okay, when you do that, okay, you will end up with okay the original equation. Okay, the original equation, this is a linear, is coming up with this okay term, okay, a into delta x by 2 into 1 minus a lambda. Okay, this is a double derivative and this is a third derivative, and the remaining is a truncation error of third order. Okay, delta x cube, delta t square delta x square delta t, and delta x t cube. Okay, now this is a modified equation. So we are starting with ut plus a ua. First thing is this term is one responsible guy and one is a another responsible guy. So in general, okay, the okay double derivative generally okay leads to give us okay dissipation. Okay, so this is okay maybe or okay, and the third derivative is generally comes with a dispersion. Okay, so mu generally okay coefficient and mu is okay dispersion coefficients. So how this is going to happen? Okay, this is okay this amount of this coefficient okay is larger and larger, then how the solution structure can be analyzed now. So for example, if you are talking about okay ut plus a into ux with this kind of an initial condition, okay, what is the solution structure? After a certain time it should be the same. Okay, but if there is a dissipation is there after a certain time, okay, you will see the solution structure like this. So the amount of dissipation is involved in the numerical scheme. This is not coming with the okay physics okay from the okay original model equation. If it is okay the third okay this coefficient, if this coefficient dominating okay in comparison to the okay diffusion term, so you some kind of dispersions like here. So this tells us that okay even if you are doing the okay finite difference approximations, okay, there may be certain okay physics okay which tells us how much amount of dissipation is involved in the numerical solution and dispersion involved in the numerical solution, and one has to take care of it. It is not random, okay, you just put it okay, numerical scheme, okay, solve it. So not every numerical scheme is not going to work out, okay. This is the thing, okay. So in general, you can also okay look and try to understand what are the leading coefficient terms when you okay do Taylor's expansion for the given okay ODEs, okay. So you can derive all the modified equations and analyze it, okay. So simplest PDEs okay can tell you okay, how to do that, okay. Why we are studying this linear addition equation in general? So for the hyperbolic conservation laws, okay, we always work with the okay systems of PDEs. So this is a prototype model in the scalar case. If you are able to understand very well, then okay we can okay expect how the solution structure of the PDEs, a system of PDEs and fully nonlinear okay exist. So this is the other way of doing the analysis, okay. So the other one okay which you know mostly, the von Neumann analysis, okay, Fourier analysis. So we are now so far in the x and t space, okay, x is the okay, space and t is the time. Now you can apply the Fourier okay transforms, okay, a discrete Fourier series. Now okay convert the okay time domain to be okay time and space domain to be frequency and time domain. Now you can talk about whether the wavelength, okay. So this is the wave propagation phenomena. So the wave, you can talk about the frequencies now, phase shifts, frequencies and so on from the physics point of view, okay. Now the thing is okay the thing here, so we are going to analyze the okay Fourier okay for a single mode of okay single term or single mode, okay, and this is generally defined by okay u and j is nothing but some okay a to the power of n into e to the power of I dot j, where a is any complex number which represents the amplitude of the wave, okay, the single mode, and capital I is here as a square root of -1, which is a complex number, and j is the mesh, and theta is the okay phase angle, okay, phase angle of the corresponding okay wave in a single mode, okay. This is okay p into delta x, p is the wave number x direction. Now okay if we apply this okay, u and j, okay, this is we define as a now a generalized term. Now okay so our Henday scheme okay okay to study the stability of the particular numerical method, okay, one substitute this trial function. The trial function is okay, this is what the trial function for the single mode, okay, to the numerical scheme, okay, and we would like to bring this kind of a form, u plus 1j is equals to a into u and j, okay. Now okay one would like to study the amplitude, okay, here a is generally called as the amplification factor. So however if you see the okay the amplitude is keep on increasing, so the energy keep on evolving, so we cannot control again here with the same okay phenomena. So the stability condition in order to okay impose or okay look into this amplification factor is stable, then one can impose okay modulus of a is less than or equal to 1, or a is okay, bounded by -1. So in simplest case we can start with forward time and backward space, okay, and here okay this is a forward time backward space. So we have a Fourier mode, okay, one single Fourier mode is u and j, then we can write down for the u and j minus 1 and u n plus 1j, okay. So this okay is responsible for the time, this is responsible for the space exponential term. So if you are able to write down okay these three and okay substitute at particular okay values, then when you do that okay this is the corresponding expression, okay. Now collect all the terms of e to the power of I theta j from the left hand side as well as the right hand side, and cancellation of a to the power of n also, okay. So you will see okay you will end up with only quantity is this a to the power of n. So this is a into a to the power of n plus 1. So you will end up with a to the power a into a to the power of n. So you will end up with this a, and okay, right hand side is okay, it's something e to the power of minus I theta. So you can use Euler formulas, right? Cos theta plus I sin theta kind of thing. So it will be okay, come as something real part as well as the imaginary part. Now okay, since okay a is a complex number, so I would like to see whether modulus of a is less than or equal to 1 or not. So it's a complex number, so square it, okay, the real part as well as the imaginary part, and okay, this is the calculation now. Okay, this is the real part and this is the imaginary part, squared and squared. So use the trigonometric identities, then somehow you will bring okay the finalized form as 1 minus 2 lambda into 1 minus lambda and 1 minus cos theta. Now if okay this quantity is greater than or equal to 0, okay, then you can say, and less than or equal to 1. So obviously you can say this is less than or equal to 1. So again, under the CFL condition, okay, 1 minus lambda is always bound by okay, so greater than or equal to 0, okay, and 1 minus cos theta. So theta depends on the theta now. Okay. So under the condition of this, okay, the both the conditions, okay, the and the CFL condition, and this term is going to be less than or equal to 1, then immediately you can say okay, this scheme is okay stable in with respect to this Fourier series. Okay, and okay, here the one note is that okay, in general for the practical problems we won't talk about. See, this is the so we discussed lambda is equals to a to delta t, but delta x is bounded by 1, and similarly okay, once you calculate delta x and given a, so you can compute what is a delta t step actually. Okay, in practice okay, this is that what is theory is suggesting, but in practice we always use okay something delta is equals to constant times of CFL into delta x by a. So this constant is okay, how big we have to take, how small we have to take, it will tell us from the okay model in general. Okay, and the stability of the numerical scheme. Okay, so for example okay, I can talk about okay ut plus okay a generalized function. I can talk about f of ux is equals to 0. Okay, so if I write down the okay inviscid form, viscosity form, so f dash of into ux is equals to 0. Okay, so whenever this is the C1 function at least. Okay, now instead of a, this is the quantity. So f dash is depending on u. Okay, u is depending on x and t. So you need something maximum of this f dash of u in a function u with the domain. So rather than okay constant, okay, for the variable coefficients you have to find the maximum values. Okay, this is the okay generalized setup okay to do okay and for the practical problems. Okay, this is about the okay and similarly you can also verify all other schemes okay are stable or not by the Fourier okay series. Okay, so far we discussed everything about the linear action equation. Okay, now we would like to okay build okay second order schemes where this is going wrong and why, and what is okay something okay wrong here. Okay, the first thing is whether these coefficients, the assigned coefficients here, okay, these coefficients are positive or not, a monotonicity or not. Okay, monotonicity either it is increasing or decreasing function. Okay, in general. Okay, right. So why we are looking at increasing and decreasing functions and what is the importance here. Okay, yeah. I'll come back to this okay a little bit later. Okay, it's a straight away lemma. Okay, so any scheme okay, if you are able to write down any scheme in this form, particular form, and this is called as a monotonicity preserving if and only if all the coefficients are greater than or equal to 0. How do we prove that? Okay, so I'll start with the sufficient condition. The sufficient condition is okay, we are starting with the okay gamma okay m is positive, and okay this gamma m positive, and we also talking about the any function we can write down in the terms of psi j n is a monotonicity increasing function with respect to j, then immediately you can write down, okay, if solution is increasing, psi j n is less than or equal to psi j plus 1 n is less than or equal to, and so on. Okay. Now, okay, from this, okay, if this is keep on increasing, now you can talk about, okay, difference between any two. Okay, you psi j n plus 1 minus psi j minus 1 n plus 1, you can write down in the terms of these values. So this is gamma m into, okay, psi j plus 1 m minus, okay, psi j plus m plus minus 1. Of course, okay, the difference between these two terms is always greater than or equal to 0. This is always greater than or equal to 0, and the assumption is gamma m is greater than or equal to 0. This is greater than or equal to 0. This difference is always greater than or equal to 0. Now immediately you can say this holds. Okay, monotonicity preserved. Now this is a sufficient condition. Okay, so if you are able to write down, okay, rather than this, okay, if you have a problem with the notation, so you can write down as, okay, bk into un plus m. So m is minus l to li. Okay, same thing. Okay, instead of coefficients bk, we are using the notation, it's a new notation gamma m. Okay, so now if this is the case of sufficient condition, let us look at the, okay, necessary condition. So what is the necessary condition? Okay, we are going by the method of contradiction here. For the same monotonicity increasing function psi j n, let us assume that all the coefficients are negative. This is a method of contradiction. Okay, so if you are choosing the all the coefficients are negative, okay, now for the specific choice of this psi I n, okay, can the scheme, okay, brings up with the positive value. Okay, this is the question for us. Okay, this is a method of contradiction. So again, okay, if I choose this is the, okay, test function for example, okay, what I'm trying to give, okay, test function is for all the values, okay, let us say this is a k value, for all the values I'm, okay, feeding as a 0, and other values I'm feeding as a 1. This is the test function. Okay, just now for this test function, okay, when we take, okay, the difference, okay, with the help of the numerical scheme, okay, obviously this is gamma m, and this is the case. Now when you take difference of all these values, all are going to be 0, and you take all difference of these values, all are going to be 0 except at this point. Okay, so it will survive only, okay, j plus m, which is not equal to k. So all the values are 0, and it will be only gamma m, okay, which is a 1 minus 0 at one particular position, okay, which is going to be gamma m. Okay, now, okay, for particular case of j is equals to k minus p, okay, when I see this difference is always a positive. See, just you have seen that 1 minus 0, which is nothing but, okay, gamma m, this is always positive, and gamma p, what is our assumption? It's a negative value times, okay, positive value, which is going to be a negative value. Okay, so when we start with the gamma p is negative value for one test function, we are ending up with this is a less than 0, but we have to prove this is a greater than or equal to 0 in order to say this is a monotonicity, okay, preserving. Okay, so or increasing function. So this is the contradiction. That's why, okay, if you would like to say any monotone scheme which is, okay, monotone, okay, any equation written in this form is monotonicity preserving, providing that all the coefficients must be, okay, positive. Okay, this is one particular case. Okay, and with this, okay, I would like to give, okay, one particular theorem, okay, which is, okay, for, okay, why, okay, these schemes will not satisfy, okay, or capture the smooth extrema clear. Okay, what is the smooth extrema actually? Okay, what is the case? For example, if I talk about this, okay, it's a random function. So at this level, okay, if you implement by any kind of, okay, numerical scheme at, okay, this point, okay, wherever like positive to the negative, maybe, okay, I can say, I can talk about the okay, convex to okay, convert to convex downward, or okay, upward to the concave downward. Okay, you can see the scheme may not capture at this extrema points. Whenever this is the phenomena, okay, you cannot construct, cannot construct any second order scheme straight away. Okay, here. Okay, so I'm not discussing this. Okay, this is the proof. It's a so simple proof. Okay, I can give you a simple proof, which means that, okay, you have to again do the Taylor series expansion and compare the coefficients on both sides. Okay, compare the coefficients on both sides. So you have to say the any numerical scheme is particular order, the coefficients must be 0. So if it is a first order, coefficients must be 0, so that your truncation error is a second order. And if it is a second order accurate, up to the second order terms must be 0. But when you are doing this, okay, you will have coefficients and the relationship between the coefficients, they are all, okay, coming up straight away or upon certain conditions in general. Okay, so if you see, okay, here, okay, I'll start with this. Okay, so this is the numerical scheme so far we are writing in the terms of this. Okay, and we can, okay, do Taylor series expansion of this, we can do Taylor series expansion of this. So Taylor series expansion of this, okay, so in terms of u, okay, rather than, okay, v is a numerical solution, u is a okay, exact solution. We are doing, okay, Taylor series expansion of this and Taylor series expansion of, okay, this in time as well as the space, and substitute it. Okay, this is the truncation error, and using the PDE, okay, we'll come back, replace this ut by minus aux, and all the okay, temporal derivatives replaced by the space derivatives. Everything will come out in the space derivatives, and you will end up with this particular, okay, equation. Now if you see, all the coefficients must be, okay, 0 for first order accuracy up to the first order terms. So the first, to get the first order accuracy, you need 1 minus summation over all bj is equals to 0, and term must be 0. So which means that, okay, summation over all j, okay, for all these coefficients bj should be 1, and this is the j into bj is nothing but minus sigma. Okay, so even though if we are saying this is the second order accurate, okay, this term must be vanishes. Okay, that's a possible. So now sigma square, okay, this term should be 0. Okay, which means that we can say summation over j into j square into bj is nothing but sigma square, the coefficients. Now what we are saying, okay, this scheme is monotone scheme. Any linear scheme which is monotone means all the coefficients must be positive. Okay, so if you are considering this is the positive, what is the meaning of the positive? The case is and the second order accurate. The second order accurate, this is a term sigma square, we can write down as a minus sigma whole square. So minus sigma value is coming from the this coefficient summation over j into, okay, bj, summation over j into bj whole square. You can write down this one as, okay, square root of bj and square root of bj. So when bj is a, okay, positive quantity, square root of bj is also a positive quantity, obviously. So both are the positive, and okay, this is the square term, so you can use the Cauchy-Schwarz inequality, okay, less of, okay, like summation over aj, okay, or okay, you can use this quantity, this Cauchy-Schwarz inequality. Okay, here summation over j square to bj and summation over j into bj, but this quantity is already given by 1, okay, but this quantity, okay, is nothing but, okay, sigma square now. Okay, sigma square is less than or equal to sigma square when we apply the, okay, Cauchy-Schwarz inequality. This inequality only be equal providing, okay, either a and b are parallel, or either a is equals to 0 or b is equals to 0. So in this case you can talk about, if this is the term as a, this term is b, then a is equals to b. Okay, or we can say it's a is a constant multiple of b. This is the other case. Okay, so if you are talking about j into root bj is nothing but c into root bj, so obviously, okay, you will end up with minus sigma, you will start the square. Okay, this quantity is, okay, j into root bj, this is nothing but minus sigma from our previous calculation. This is constant multiple of root bj. So since it is a constant, you can take outside the, okay, summation, but from the order conditions you have 1, so this is nothing but c. Okay, c, any constant is equals to minus sigma, but sigma is, okay, what is a sigma value in general? Okay, it's a positive value, right? That's what we started with, but this is going to be a negative value. In practical cases this is not true. Okay, which means that any linear monotone scheme cannot be second order accurate, because you cannot able to show the second order okay, term in the Taylor series expression is 0. Okay, so this is the okay conclusion that okay any linear positive scheme is at most first order accurate. This is proved by the Godunov in 1959. Okay, any linear positive scheme is at most first order accurate. Now, how to build the okay second order scheme? But okay, whenever okay there is a smooth extrema, we are not able to compute the smooth extrema accurately, but we would like to go for second order by sacrificing something in the first order. Now this is some kind of a trick okay in the numerical scheme. Okay, so now I'll start, I'll begin with something here very basic again. So if I start with okay second order scheme, okay, so I can go with this forward time and center space. Okay, so time derivative is dui by dt and space derivative is nothing but here ui plus 1 minus ui minus 1. Okay, okay, the coefficient is minus a by 2 delta x. Now we can write down something like adding and subtracting term as ui, okay, plus ui as well as minus ui. Okay, when I take this, okay, I can write down a by 2 delta x and take the common term as ui minus 1, and this is going to be a coefficient 1 minus ui plus 1 minus ui by ui minus 1. So if this coefficient term is positive, okay, then we can say the scheme is okay monotonicity preserving. Then we can say the second order scheme is also a monotonicity preserving. But this is not true. Okay, now that's the case. Okay, we are writing second order scheme in terms of okay first order scheme. Okay, now what is the case? Okay, here we are defining this okay ui plus 1 minus ui by ui minus 1 as some ratio between two consecutive okay grids, and they are okay slopes actually. Okay, and as a ri, so if ri is less than or equal to 1, okay, we can able to control, otherwise it's not. So that's why we can I say okay, see for example here okay, this is let us say okay ui plus 1 minus ui minus okay slope, and this is ui minus 1 slope. If this two slope okay less than or equal to 1, okay, it is satisfying the okay so monotonicity of the solution. Okay, now if this is the case, okay, this is the slope 1, okay, ui plus ui minus 1, and if this is the bigger, so suddenly this slope changes its sign generally, so you'll have okay this point. Now at here okay you have something overshoot. This is the one case. Okay, this can happen in other way also, right? This is also a possibility. This is also a possibility. So you may encounter the overshoot of the solution or the undershoot of the solutions. Okay, in principle I can say okay how you can see the solution. For example, okay, you are okay taking the square pulse and approximating it by okay a numerical solution, you may encounter small okay bump. It's a wiggle. It's a wiggle. Solution is everywhere looks good apart from where this transition is happening from discontinuous to the continuous and continuous to the discontinuous, because the slopes will vary now with respect to this scheme. Okay, or you may also see okay, may also see in the numerical simulations, if this is your exact solution, okay, maybe okay I can talk 1 second, talk about, you may see okay maybe like this. These are called wiggles actually. Okay, these are called responsible for this wiggles type of solution structures. So one has to be carefully design the schemes. Now if you see this okay, and okay if you are defining a as okay ui plus 1 minus ui and b as ui minus 1 as these two consecutive slopes okay or successive gradients, okay, and okay the first condition is okay this should be less than or equal to 1, that we will define. Okay, so to construct any second order scheme, okay, So select any first order monotone space discretization, generally the first order discretization as a reference, and write the higher scheme as the monotone scheme plus some additional terms, and multiply by the additional terms by a limiting function psi, then express in the terms of successive gradients. Then okay, you are going to introduce some kind of a switching functions you have to control in order to control the numerical solution now. Okay, so simplest case, okay, I'll start with this thing. So if I start with this dy by dt is nothing but minus a by 2 delta x, and this term, okay, you take any monotone scheme, you can write down in the terms of this way, okay, ui minus 1 minus ui minus 1 into a plus 1. Now okay, you can see here minus a by delta x into ui minus 1, okay, sorry, yeah. So I'm taking some part. This is 1 and 1 by 2 term is over here, 1 plus 1 by 2, which is going to be 3 by 2 term. So I'm writing as a first order monotone scheme and the first part, and okay, here is the rest of the part from this. Okay, now I'm able to write down okay any second order scheme. This is the second order derivative. Okay, this is the one sided derivative. Okay, we are able to write first order term plus some kind of correction. Okay, now okay, if you are taking these coefficients ui minus 1 and ui minus 1 ui minus 2, so we are finding the successive ratios. These are the Ri is the ui plus 1 minus ui by ui minus 1, and replace by I minus 1, you will get Ri minus 1. Okay, so now what we are writing, okay, so rewriting this equation okay with respect to this in the terms of Ri. Okay, so ui minus 1 and ui minus 1 ui minus 2 if I take, and I am bringing some kind of functions, okay, psi of Ri and psi of Ri minus 1. Okay, this is Ri minus 1 and Ri. You take any kind of a function there which is in terms of Ri and Ri minus 1, so that okay this denominator and this denominator will get cancels off. You will have some okay, let us say if it is a linear function, let us say simply an Ri in general. So this term and this term will get cancels off, okay, and this term and this term will get cancels off. It will come back to the original scheme. But our motivation is not that, okay, we would like to see this second order term should be controllable, but first order term plus some additional term. Okay, now this term you can inject, okay, this is a generalized function. Why should I take is only the linear function? I can take any function. Now I can count this function, the idea, okay, psi of Ri or psi of Ri minus 1. Now if I take it and I can able to write down an entire second order scheme in terms of the first order scheme with some constant multiple. Now if I am able to control this somehow, okay, then okay I can build second order scheme. Okay, now the case is okay, so what are the choices now? Okay, if this is a monotone scheme, this should be greater than or equal to 0. So obviously I can start with this point, then I can come up with the condition that okay on psi, okay, what are the conditions? You any function, any either it is a linear function or non-linear function, if it is satisfying this particular property, then you can able to build a second order scheme. Okay, now okay, but how much freedom we do have? So there are many ways to construct this particular function. Okay, so simplest case is given by the Van Leer in 1979 to 1983 in series of 5 papers. Okay, so the first thing is okay, this psi function should be always a positive function. Okay, r is greater than or equal to 0, and okay psi should be 0 whenever it is come back to the first order scheme. So first order scheme plus second order scheme, we require some kind of a blending in between this or switch. Okay, now okay, so I'm not talking about all these conditions. So if you are able to see these conditions, okay, the final conditions, the proof is already there. So if psi of r is always greater than or equal to 0 whenever r is greater than or equal to 0, and it should be 0 when r is negative, okay, and psi of r always should be between, okay, 0 to 2 or 0 to 2, and okay, in principle you can combine all these conditions as whenever the psi of r is in between 0 to minimum of 2 comma 2r, you are able to construct a second order scheme which is given by Van. So what is the class of functions where you can take this class of functions? Okay, psi of r is nothing but r and psi of r is nothing but 2r. If you see this diagram, okay, this is okay, psi of r is nothing but r and psi of r is nothing but 2r. Okay, so the minimum of r comma 2r, okay, 2 comma 2r. So if you take any function, okay, you take any function, okay, psi of r which is within this region, okay, it will satisfy all the properties of the above, okay, conditions. Then with that we can construct a second order schemes. So there are many versions, okay, so there are many versions. So I like to okay, tell there are many versions. So one is the Van Lee limiter, okay, this is one of Van Lee limiter. So some portion is here and some portion is here. This is the curve, they are fitting in that region. This is one of them, okay. The second one is, okay, min mode limiter. So this is the min mode limiter only, okay, I mean, okay, specifically. So which satisfies all the properties of this function, okay. So there are many, okay, super B limiter and general beta limiters, and one is Osher limiter, okay, and okay, maybe, okay, Somasundaram flux is also there, and okay, I think Professor Dubey also, okay, introduced some limiters, okay, in 2005 and 2006, okay. And when you see the solution structure, obviously with the different type of limiters with the sinusoidal okay, initial data, you can see, okay, here in the diagram that, okay, the first order scheme which is the, okay, A part, and B is the second order affine scheme, okay, and the third one is second order affine scheme with min mode limiters, and second order scheme with the B limiter. So the more effectively you construct the limiter, the more close the solution to the smooth extrema here, okay. So for example, if you see here, okay, here also, okay, min mode limiter you are not able to see the close to the solutions, but here you are able to see, okay, yeah. So even for the discontinuous data also, okay, you can see, okay, you can see as you are changing the limiters, okay, I think limiters will be, yeah, again with the min mode limiter, okay, sorry, second order affine scheme with the min mode limiter which is a C, and second order affine scheme with the Van Lee limiter which is a D, and okay, the another one is a super B limiter which is a D, okay, E. You can see as long as you are changing the limiters, okay, you can see the solution structures which are really nice, okay, that you can, okay, play over there by constructing a suitable function section, yeah, yeah. So this is what different kind of limiters here, okay, you can see all the limiters when it's applied to the discontinuous data for the linear direction equation, okay, the appropriate initial conditions as well as the boundary conditions and all of them, okay, yeah. So okay, it's fine. So I have time till 10:15, right, Sadiq? 10:15, I have till time, right, 10:15, okay, okay. So okay, I think I can add some new definitely. So I think, okay, okay, I thought, okay, I can cover that lecture also, yeah, fine, yeah. So I think you will see in the rest of the, okay, topics how to solve this equation 1, ut plus f of ux is equals to 0, u of x comma 0 is nothing but u naught of x. Now finite difference schemes have certain limitations, then how to build it and okay, how to analyze it, you know. Now I think Professor Gowda, he may talk about the finite volume schemes, okay, which are nothing but the conservative finite difference schemes now, and the higher order versions will talk about by this Professor Naveen Garg from IIT Kharagpur. Yeah, so that's the thing. And okay, if you see, okay, this is one of the Ritesh paper, Professor test paper. So you will see the limiters in the functions. Yes, you can see the scheme to be particular TV total variation diminishing if this constructor function phi should sit in 0 to 2 and 0 to 2 by theta. This is one of the case where he proved in his PhD during PhD. Yeah, the derivation is more or less same. Okay, you can see 0 is less than or equal to this pi comma pi theta is less than or equal to 2. Okay, one of the paper. Okay, so now the proposed TVD region is something new. Okay? This is what you have seen just now from the TV Swabius diagram. Now is the new, but this is for non-linear PDEs. Okay, what I have shown it for the linear PDE. Okay, yeah. So obviously, okay, you can see the numerics also from his paper. Yeah, a different type of limiters is applying. Okay, can get the solution structures. Yeah, proposed limiters. Okay, proposed limiters with delta is equals to 9 and delta is equals to something 1. The top two. Yeah, this is one particular paper, and the particular paper is he will discuss also flux limited schemes. I think Professor Gowda. Okay, these are slope limiters. You can also play with the flux now. Okay, the same story. Okay, again the functions be same. Yeah, these are the some kind of limiters she has done. Maybe it's a motivation to study this basic papers after the literature. Okay, maybe 80s. Yeah, yeah, that's it. So the in order to see the solution structures for a higher order, this is a finite difference. Now one has to see in the finite volume first. Okay, what are the advantages, disadvantages of the finite value? Then if there are any failures, then the new schemes will come in the picture again. So it's a keep on going. Okay, so finite difference techniques are easy to extend it to the multi dimensions, but finite volumes is really tough with the code and evaluation and also time of executions. So the alternative techniques are there, which are adapted. One of them is discontinuous Galerkin techniques, which is there, to solve this system of PDEs in multi dimensions. So far it's early late 50s. So it started in 1954, I think we can say, until 1980. Says first and second order scheme developed. Then from 80s to 96, so third, fourth, and fifth order schemes are developed. Then then thereafter the story is all the higher order schemes and their complete manipulations. How to get the better solution? How to improvise it? Yeah. So the story is whatever I have seen shown that this in the finite volume schemes there are two classes of schemes. One is affine type. It will take only cell values. It's again Professor Gowda will talk about it. I don't know. See, so in the finite volume, basically you are going to discretize the PDE by a values. Xi minus of 2 xi plus of times t into tn plus 1. So you are going to discretize the PDE in this domain. But this is not the only way. You can do in other way also. So this is something. So in the finite volume you will do discretize in plus 1. This is this class of schemes generally called as affine schemes. That's there is a math. So you can also discretize which is also you can say it's a conserved in this. Whatever the value which is entering at this point leaving at this point is generally called the conservation loss. So there are two schemes. One is affine, the other class is central. I think in this workshop you will see this affine schemes on. Okay, that's all. If you have any questions, you can ask. Yeah. So did you get the notes? Okay. Yeah. Read and find in 2-3 textbooks. Okay, maybe I'll suggest, okay, if you would like to see, the one thing is Charles Hirsch, okay, finite value methods for computational fluid. The second thing is talk about this CB Lane, computational gas dynamics, and okay, obviously the okay R.J. Levick, numerical methods for conservation laws, and okay, this is numerical methods for conservation laws. Lecture thing is finite value methods for hyperbolic problems. Okay, this is the text for the basics, okay, in order to understand scalar cases, okay, some linear cases. Obviously, for understanding the systems, you have to go with the Toro.
So if you have any questions or any doubts, you can ask the speaker. Also, he can help you with your research direction also if you are working in this particular field. So please feel free to ask him if you have any doubts or any questions.
Okay, so either I should have said they understood everything or they do not understand.
Yesterday, and we hope to have him again in future for any other conference or workshop. And now let us honor the speaker with some small gift we have. Yeah, please come.
So I'm logging out from here.